Okay. All right. So what did we do last time? We considered variational approach, right? And so we then today look a little bit more on the applicational side of things, and we'll start with considering the Born-Oppenheimer approximation, which can be put in the context of variational approach as well. Essentially, many things can be put in a context of variational approach. So that's why we were studying it. It's a really powerful principle. Okay, and as I was commenting last lecture, classical mechanics also can be put in a variational context. And maybe we will touch upon this subject if we get a chance to study path integrals approach to quantum mechanics. But for now,
Path integrals?
Path integrals, yes.
I'd like to encourage that direction.
Okay, good. All right, and then we'll have a really general view on both quantum and classical, because path integral approach is the only approach, in my knowledge, that kind of bridges formally at least at the physical level of rigor, the classical and quantum mechanics. I think mathematicians are still not completely happy with this infinite dimensional integration, but physicists at least use it. Yeah, it works, exactly. So that's all physicists need. All right, so then we proved that the previous lecture is that, say, if we do this with a trial function phi, that is equivalent to essentially saying that the first variation of energy is 0 and energy was defined as like this, right? And so what I want to start with today is to show practical applications. The simplest, of course, is when we have our phi equals to some linear combination of, let's make them phi's like that, small phi's. These are some basis functions, and the coefficients are the only parameters that we can vary. Okay. It's okay. And what I want to show is that if we do that, then we obtain exactly the same as we obtained before using the Dirac projection method. And we'll talk a little bit about that. So now first, let's consider if we start with this construction, right, and put it in our variational principle expression, right? Then what equation for the coefficients will we get? Okay, and the way the variation of phi function can be done here, it's very straightforward. Essentially, we treat these parameters, they are constants, right? So variation will end up being just partial differentiation with respect to these coefficients, okay? Yeah, please come in. Extra 5 minutes for people from Mississauga. We can give extra 5 minutes for people from Mississauga to get themselves comfortable. It's a long way. All right, so this is our variation, okay? And then if we plug this and this in our expression, then what we have going to be sum over I, delta Ci, then d phi dCi, h minus E. Then there will be another summation inside, because these summations are independent. And this should be phi Okay, so this is 0. Now, what we can see is that this partial derivative is just going to be one particular function, right? So the df partially differentiated with respect to ci's give us phi I, and this sum then will be right. So this is some variation of the coefficient. We do not specify it when we don't need that really. Any coefficient variation. And this is just a function in front of the coefficient, right, that we vary in this sum. So then with this in mind, this expression becomes sum over ij delta ci phi I h minus e, and then phi j cj. And, well, strictly speaking, there should be conjugations, because we've taken this from the bra part, right? It should be conjugated. Now, all these variations, they are independent. We can vary only one coefficient at a time, right? And so also they are arbitrary. That means for any I, that's the, we single out I as a variation, right? Then we have phi I h minus e phi j cj equals 0. And then we have a summation here over j. So we cannot remove the j summation, but we can remove I summation because all these variations are independent. Yes?
Over there, is that a phi or a psi for j?
This one?
Yeah,
It's
shouldn't it be a phi?
It's a phi j, yeah?
Oh, because it looks like a psi.
Okay, so far we didn't introduce any psi.
Oh, sorry, no, like with that one.
The phi,
Shouldn't it be different is what I'm saying.
It's two different ways of both varying.
yeah. Okay, so this is supposed to be a big phi.
No, I don't mean that one. I mean.
It's this one. And then these guys are the basis functions, right?
But shouldn't that one that you just made an arrow from be the this one?
This one?
Yeah.
Well, it was, really. We just expanded. So, yeah, you're right that we started with big phi in the ket, right? Mm-hmm. And then essentially our way of thinking about this phi is in this linear construction fashion, right? So we have a linear coefficients in front of the basis functions. So that's how we present our trial function, big phi, right? And then whenever we have phi in the expression, we can substitute it by this sum then, right? So we just made this substitution that makes our construction concrete. Like before, it was some trial function, a trial function. But here, it is now the trial function because it has a structure. We haven't defined yet these basis functions, but there are some bases and some coefficients in front of them, right? And so we vary only the coefficients in front, and the basis is fixed. So to be less abstract, you can think of solving the problem with a particle in the box, and the potential inside of the box, v of x, is equal to alpha x, all right? So that problem can be solved as, well, the eigenfunction for this problem can be looked as a linear combination of basis functions for just a normal particle in the box problem. So these phi i's, they are eigenfunctions for our particle in the box function, and the phi is the function that will be a solution for particle in the box with a potential which is linear inside of the box. Okay, So outside of the box, they're identical. The potential is infinite. Okay? Now, we did all that, and then we said, OK, so these are independent. And that's why we can go and consider them independently. For every I, we have this expression. And since again, these guys are independent and they can be varied in any possible way, then for this to be true, we need to have sum over j, phi I, h minus e, phi j, cj to equal to 0. Okay? And this is pretty much the same as doing the projection. And that's for any I, right? So the projection method, which we used, I think, before, starts with, say, this expression h phi equals e phi, right? And just formally, if this is an operator acting on a function, it will produce some function f. And this is another function, g. Right? So I write them differently because, well, if we do not think about the other side when we consider one of these sides, then they're just some well, differently looking functions, f and g. Now, for f and g to be the same, that's what we want based on this expression, right? We can either use coordinate representation, write f of x and g of x, but we are also familiar with Dirac's notation, right? And expansion of any function in the basis. So now imagine we have a basis phi I of x. Then we can represent f of x as a linear combination of some coefficients phi of x, right? And g of x as some other set of coefficients, but the same basis, right? Now, if I pose the question whether f and g are the same or not, in terms of these expansions, how would you answer to me? When f and g are the same?
Each individual coefficient.
Yeah,
Term by term coefficient.
that's right. So ci should be equal to di for any I, right? So that means that if we have a basis set phi I, for two functions to be the same, the coefficients must be the same. The same as with vectors. For two vectors be the same, the coefficients for these vectors in the same basis should be the same. Right? It's very straightforward. Now, then, how do we find these coefficients?
We take the inner product with
Inner product, right. So how do we form inner product? It's the integral, right? So we form integral. To find the coefficient, we take phi I star of x, f of x, and that gives us ci. Right? So then you wouldn't be surprised then, after this consideration, that if we have some function phi that we expand as, well, to make it, I guess, slightly more different than what we have here. Say phi needs some other expansion. Well, let's say it's ci with tildes. I just don't want to confuse the ci's here and ci's in the f expansion, because this is the expansion for different functions. Right? So if, say, you expanded phi, and then you acted with h on phi, right? This is a function which is sum over ci tilde h phi I. And then another side of this story is e phi, which is just e times sum of ci. Now this is your function g, right? And this is your function f. And following this logic, we want to compare the coefficients of f and g in the basis of phi i's, right? And so how do we do that? We form these inner products. And in these terms, that will be multiplying with phi k, some arbitrary k, right? Multiplying from the left both expressions, that is like this part, right? And integrating with dx. And we're asking that this will be exactly equal to dx of phi k star e phi, right? And then if we put instead of h phi and e phi these expansions, then we get well, I will substitute integration by the Dirac notation, right? So that will be projection with phi k from the left, and you will have h. The phi is expanded now, phi I, ci. That's going to be this part, right? And you need to sum over I for any k. This should be equal to projection and sum over I phi k. The energy goes out, right? And if we combine those two things together, the equation will be h minus e, right? So we arrived to the same expression up to, well, substituting the subscript letters, I to j and I to k. All right, so this is more known in the literature as Dirac's projection method. And this we obtain just from the variational approach with linear construction. Okay, so they coincide, rightly so, because, well, they both solve our problem in the subspace of the full space. So the subspace we are considering is the one that is spanned by our basis functions. Okay, so what this expression tells us, that this function and these functions, they are exactly the same based on the coefficients that you obtain with the basis functions. And so if your basis set is complete, in other words, if these summations can go up to infinity, right, then it's exact representation. So either you solving the problem in the coordinate representation or in the basis set representation, it's equivalent. But if these summations are finite, say you use finite number of basis functions, then this part and that part can be different. It's just based on these coefficients, you won't see it, because the coefficients only care about specific projections on the specific functions. And if the difference is outside, so say you have two vectors on this board, and they look exactly the same in the basis of the vectors which are in plane of the board, right? But they are different. One looks to you, another looks from you, right? So you won't see that based on the projections to the vectors of x and y, which are analogs of these functions, right? You won't distinguish the difference between, say, vector v and vector u, because you only will know, if you operate with x and y, the projections of x, v and u on the board. But what happens in the outside of the board, you don't know based on, well, you're just two-dimensional person who say lives in the board, on the plane of the board, right? So you won't see the difference then. And the same here, you will solve problem approximately based on the basis that you set up initially, right? And if your basis is poor, then you will miss some differences that appear because the basis doesn't represent the full picture. But if the basis is complete, then the solution will be exact. Okay? So these two are the same. Algebraically, then what this means is that if you start considering these functions, depending on whether they are orthogonal or not, if we consider the completely general case, functions phi and phi j, they may not be orthogonal, and then what you will obtain is phi I, h, phi j, cj minus or equal to sum over I, phi j. Okay? And this we can call now Hij, matrix of Hamiltonian. And this one is the overlap matrix. Right? If for a particle in the box function, this overlap matrix will be delta Kronecker Ij, right? For some arbitrary basis, it may not be. Okay, and then we can write this expression differently in the matrix vector form. So you have a vector C multiplying matrix H, and you will get E as matrix. We got Cj here, and that's sum over J. Right? So this is a so-called secular equation. The way to solve it, it's just eigenvalue problem, right? So you can diagonalize H, and then that allows you to obtain the eigenvectors for the problem. Okay? This is called general eigenvalue problem. Because you have a S matrix, S is not equal to identity. But this can be turned into simpler eigenvalue problem with the same eigenvalues, with a simple trick that the C must be multiplied by S1/2. That gives C prime. With this substitution, what we can do, we can write H being S minus 1/2, S1/2 C. This is just identity. We can put it anywhere. I'm just recreating this expression. And then I split the S to S1/2 times S1/2. Okay? This is also valid because S in the first power, so I just made two square roots of S multiplying each other. All right? So then I notice that this is a C prime, and this is a C prime. And all I'm missing is my new Hamiltonian. And I want to get rid of this guy, right? So how do I get rid of this guy? I multiply the whole expression by S minus 1/2 from the left. Okay, so this whole expression goes here, and I multiply by S minus 1/2. So what I get is S minus 1/2 H S minus 1/2 C prime equals to S minus 1/2. E is a constant, so it commutes with matrix multiplication. And here we already have C prime. So this can be made as S minus 1/2 S1/2 because E commutes with it, right? And then we can safely say that this is 1. And this is our new Hamiltonian, H tilde. So we get H tilde C prime equals to E C prime. So this is kind of a standard eigenvalue problem. If you set up the H matrix, then you can find the C and E's in MATLAB, for example, with Eich function. Okay? The syntax, I believe, is like this. Here, instead of U, you can put the C prime. So eigenvalues, eigenvectors, matrix H tilde. And once you obtain the C prime, then you can go back to C's by multiplying with S minus 1/2. Right? Okay. Now, the same trick can be done for time-dependent case. In the sense that we can either start with, say, let's put psi h minus I d over dt. This is our variational expression. Psi can be made as a linear combination of C and T's, some basis.
Why do we have minus I with the question of T?
Because this comes out of, oh, this is a variational principle, it's equivalent. Variation of J functional in the Dirac-Frankel variation principle. J was defined by psi h minus I d over dt psi, and this was equivalent solving h psi
Yes.
time-dependent Schrödinger equation, right?
Yeah.
So eventually the variational expression for finding the parameters in psi that govern the time evolution are coming from this expression. And the simplest, again, construction would be the coefficients in front of the some basis functions, right? And then we vary psi in the same way by summing over variations in Cn, d psi over dCn, which gives us back phi n x, right? Going through the whole algebra, which will be exactly the same as in the previous case, we would obtain something like phi n h minus I d over dt, c k phi k, sum over k, for any n 0, and then we can do the differentiation because we know that only c's are dependent on time. H will be going through the c's, and so what we will get is phi n h phi k ck time dependent sum over k minus I d over dt. Sorry, that's going to be I, this product, and then derivative of ck. Right, so this is equal to 0. What does this give us? It gives us a differential equation on the coefficients. Okay, so it's first order differential equation. We can rearrange terms and put them in a matrix form. So there's H matrix multiplied by C, and then it's equal to I S matrix, and then C dot, which is derivative. Okay, let me write it in the form of the derivative. Right, so this is the expression, and then you can write it down as I dc over dt equals to S minus 1, inverse of the overlap, Hamiltonian, and then coefficients. Okay? And if your basis set is orthogonal, then the expression is very simple. It has only H matrix, right? And this is orthonormal basis. Okay. Now the same result can be obtained if we just start from time-dependent Schrödinger equation and project based on the same logic as we explored in the time-independent case. We project with basis functions and make sure that so H psi equals I d psi dt. Right, so you can do the same projection, phi k, and then here phi k, right, and make sure that for every k you have the equality of the left-hand side to the right-hand side. Yeah.
And so just going back and making sure I have it clear, that C vector is a vector of all the coefficients.
That's right.
For our expansion. So it would make sense that C vector obeys the Schrödinger equation because in a sense that C contains all the information for our state vector.
That's right, yeah.
Cool.
Yeah. So now, do you know how to solve this equation? If you have first order it's a first order system of differential equations. Practically, how would you solve it?
I mean, my first thought is multiply the vector with the matrix on the right-hand side, and then you just have a bunch of first-order differential equations. Maybe this is a better way?
Well, let's consider, because it's important to kind of be able to do this practically, even for the simplest possible case. Say, simplest possible case that still has the matrix form would be to have 2 by 2 case, right? So you have these numbers that are coming as the integrals of your basis with the Hamiltonian, right? And then your coefficients, just two functions of time. What you ask to solve is this derivative of these coefficients. To put it explicitly, it's I multiplied by dc1 time dt and dc2 time dt equals to this 2 by 2 matrix c1 c2. How do you solve it?
Again, I would like to multiply out the right-hand side, and then...
You multiply this side, right-hand side, by...
Well, I just multiply the matrix and the vector and the matrix together to get a vector.
Okay, so, sure.
Is that a bad idea? Or do I want to multiply the inverse of the Hamiltonian on both sides? Really, I don't know. I would just hit it with a stick until something happens.
Yeah, all I want to know is what kind of stick are you going to use. integrals.
There'll be two. I mean, we have a system of first-order differential equations.
Yeah.
And they're all linear, so it's easy enough to solve. It just
Yeah.
needs to work.
Yeah, that's why I'm wondering why does it take you so much time to answer my question?
I mean, I have to write up the steps.
What steps?
Again, so multiply h. So we have h1 times c1 plus h21.
Okay. Oh, okay. So you want to get the vector. Okay. So the vector. Sure. Say you got your vector. What's next?
Then so we have two equations essentially. If we take the difference of those two equations,
Uh-huh.
on the right hand, that doesn't. We have to do some multiplication of like elements. But you want to.
What would be the purpose of those multiplications?
I want to make a linear combination so I can get rid of both of the c1s.
Okay.
Right?
And only live with the C2, right?
And then I could integrate.
Right.
There.
So what essentially you're trying to do is diagonalize the Hamiltonian.
Sure, but that's a much easier way of doing what I was trying to do.
Yeah. Right. So if you diagonalize the Hamiltonian, then you could essentially obtain the form that will be something like C1 tilde, C2 tilde. The tildes are coming from the fact that in the original representation, phi 1 and phi 2, the Hamiltonian is not diagonal. So you need to switch the representation to the rotate essentially in that basis of phi's so that your Hamiltonian would be diagonal. And that actually corresponds to solving time-independent Schrödinger equation. Right? And then if you are presented with this equation, then C1 doesn't care about C2 and C2 doesn't care about C1 because there are no terms that couple them. So you can easily just write dCj tilde dt equals to Ej Cj, where j is either 1 or 2.
So how would we actually diagonalize the matrix then?
How do we diagonalize matrix? Well, that's a standard procedure. You
find the eigenvectors and
eigenvalues, right? So
okay.
make a unitary transformation. But your way with the multiplications, that's what. Well, but that's what happens inside of your computer when you press enter on the Ike statement, right? So it's essentially a series of multiplications.
My one question though, so multiplying on the right hand side, sure, we put the unit in the inverse, okay. But then when we multiply on the left hand side, does that derivative get in the way and that's all that I'm concerned about.
Okay, yeah, that's the right concern. Because the concern stems from the following observation is that okay, so in order to get this E matrix, right, in order to diagonalize Hamiltonian, you need to multiply Hamiltonian by unitary transformations. Let's write them this way, right, for Hamiltonian. Now, okay, that's good. Now let's see how do we transform our expression, because what we started with was this, dc dt equals hc, right? Now we want to get to the E part. How do we do that? We multiply by u on the left. We multiply by, well, wait a second about the right part. That would be a wrong thing to do because, again, n is in a transformation from the generalized eigenvalue problem to the normal eigenvalue problem. What we could do is we put here u dagger u. Right? That's the trick. It's since it's a unitary matrix, then transpose times the matrix gives you 1. So you can put 1 anywhere in multiplication, right? So then what you have is going to be that you have u. I can be taken away because it's a constant kind of will be commuting with everything. Then you have dc dt equals to UH, U dagger, UC, right? So this is your new Hamiltonian, which is diagonal E, right? We chosen U's to be that way so that they diagonalize Hamiltonian. So then they give us diagonal form E. Now, the only trouble is that we're not dealing with C's anymore, but we need to multiply C's by U, right? And that's why I switched to the C tildes here, right? So this is our new vector. This is diagonal, nice. And then this thing, it must be also, well, considered to be something like I d over dt UC, right? If we can do that, if we can consider this as derivative, time derivative of UC, then we're done, right?
Do we use like the product rule, some kind of funny trick there?
Right now, I'm just doing wishful thinking, okay?
Oh,
okay, so I'm doing wishful thinking that in the sense that the right-hand side is nice, right? We have diagonal part times some new variables which we can obtain as long as we know, if we put the C there, we know presumably U, so that's our new C's. But the left-hand side, in order to be completely kind of equivalent to what what I wrote at the end, or what we had before, just with the Hamiltonian that wasn't diagonal, is some I times d over dt over new variables, UC, right? And so then, but here we have something different. We have U outside of the differentiation. So then the question is whether we can go from here to here and say, okay, that's it, we're done. Or we need to consider the derivatives of U. Because that's the only thing that stands on our way to equate this to that, right? And that's a very important part, because this thing is IU dc dt, that's what we want, plus I, okay, so du dt c, right? We would need to differentiate the matrix U with respect to time, and then multiply the coefficients. So what are we going to do with this part?
You're going to hope that it's 0?
Yeah, but we don't hope we know that.
Oh, because U is not an explicit function of time?
That's correct. Why is it not explicit function of time?
Because it's made up of eigen.
Huh? Sorry, say it again?
They're made of eigenfunctions, and functions are basis functions.
Well, close, but not entirely true, because yes, it is the U is chosen so that it's the set of coefficients that makes our basis that we started with a basis of eigenfunctions of H, right? Now the question is whether these coefficients are changing with time or not. But why would they change in time if all the job that they need to do is to just diagonalize H, and H doesn't change with time, right? So then the eigenfunctions should not change with time.
So wait, so we're talking about the time independent case?
Hamiltonian, yes.
I see. Everything is good.
Everything is good, yes. So if H is time independent, everything is good.
Yes.
Now if H is time dependent, then you cannot neglect these terms. Okay? So for time-dependent H, your U's will be time dependent as well, right?
Yes.
And so only for a particular moment in time, you will be able to find eigenvectors, right? And then the next moment of time, the H changed, so you need to find new U's, right? And this new U's then will be different. So now we can consider that case as well. It's nothing but just slightly more involved algebra. But the idea is very much the same. If we have now H that depends on time, U will depend on time, and then all we need is to treat this term, right? Because this is still true, Okay, and we can make an expression for the part we have here, right, as this minus that, right? So then, what do we have? It's I d over dt. Is everyone can follow? Because okay, good. So okay, so we have this. Right, so UC minus I d over dt. This can be useful, this whole case of the time-dependent Hamiltonian can be useful for the consideration of, say, nuclear dynamics when the electronic dynamics when nuclei are considered as parameters in molecules, for example. All right, so we have this, that, okay, and this is equal to our E's that now are time-dependent, and then we have UC. All right, so this is diagonal times UC. And this is all good. All we need is to modify this term so that it will have UC form, because then we can call UC our new variables. Okay, and it's very easy to do. You just put UC as it was there and multiply by U dagger, right? So then this is a identity again, right? And then the whole term becomes du over dt, U dagger. So you call this as a new quantity, UC, right? Your variable equals to E over t, UC. All right, and then here you have d dt, UC. Eventually, this is a new vector. All right, so it's like there's no minus here, and we can put these guys on the other side and call this thing now C tilde. So say C tilde is our UC, right? Equals to I du dt cross C tilde E t C tilde. Right. So it's like time independent case, but there is this term that is responsible for the fact that your basis is also time dependent. Okay. And this is actually something that is related to non-adiabatic terms in Born-Oppenheimer representation or adiabatic representation, or in physics they are also called non-adiabatic because essentially if you probably heard that word adiabatic in thermophysics, right? So adiabatic means that the heat doesn't escape the system. But if you go to the definition what adiabatos means in Greek language, it's essentially says that the translation would be that you are confined to some area, some space, something, right? So you're confined. And here the confinement is to the particular electronic, or not electronic in general, it's a particular eigenstate of the Hamiltonian. Because if you start your evolution, your initial conditions for this problem, so that the C1 tilde is 1 and C1 tilde, oh sorry, C2 tilde is 0, right? So you're starting and evolving with just with this phase factor essentially, right? Then you would keep doing that, and the only thing that will kind of leak the population from the first level to the second level is this term, because this guy is diagonal, and so whatever you have in C1 will stay in C1, because the solution for diagonal equation is very simple. C1 at time t equals to exponent of minus I e e1 t C1 0, right? So that's the solution, and that's solution for actually both of them, either 1 or 2, doesn't matter. So whatever you start with, this exponential factor will just create the phase oscillations, right? And then the Ci square in time will be constant, 1 or 0, because this won't affect the absolute value, right? So you're confined. Now these terms, they inherently will have some off-diagonal terms, and those terms kind of allow you to leak some of the populations meaning the absolute value of the coefficients, because they characterize the probability to find the system in a particular state, right? So we call them populations in jargon. Right, so then these terms, they will have some off-diagonal terms. These are matrices U, so they have diagonal and off-diagonal terms. And then they will transfer some of this population between the levels. Okay? Now, the trick, though, is that if you evolve in time slowly, then this derivative can be made as small as possible, potentially. Right? And so then, since it's a derivative, you can make this transition relatively small. Okay? And if you evolve slowly, then you will evolve on a particular state. All right? Okay, what else? I think. All right, so that's why it's non-adiabatic, because those are the terms that allows you to go beyond the state where you are in, right? And these terms can be reduced or enhanced based on how quickly you are moving, in time. And that movement in time usually depends on the parameters of the system. So say if you have electronic subsystems, electronic levels, then the motion of nuclei, they regulate how quickly these derivatives are evolving, essentially. All right, so okay, so next topic will be the two-dimensional problems, because that's where we can see problems with variational approach and how we can cure some of these problems. Let's make a quick couple of minutes break so that I erase everything. You guys have water or something. All right, let's resume. And one of the biggest problems of variational approach is that the computational cost grows very quickly with dimensionality. So if you think about the same particle in the box with now two-dimensional bottom or two-dimensional box, right? And you put the potential to make it interesting. Potential will depend on x and y, alpha times x times y, right? Then you could approach the problem in a similar way. Your phi x y is now sum over ij, cij, phi ix, phi j at y, right? So this can be particle in the box functions for 1D problems, or you can think about this more like either one particle in a two-dimensional box or two particles inside of a one-dimensional box that interact through this potential. Okay, so it doesn't really matter. The point is, if you start increasing the number of dimensions or you start increasing the number of particles that interact, then to represent the functions of two or more variables, you need to essentially construct all these products, possible products, in order to cover all the possibilities, right? Because this set potentially is a complete set in X, this set is complete set in Y, so you need to make a product to make a complete set in X, Y, okay? And so if I goes from, in the practical calculation, from 1 to n, where n you can think of 10 or 100, some big number, and then j goes from 1 to n, then ij goes from 1 to n squared, right? So, and as you can imagine, if we start thinking about real molecules, which say like CH4, methane, right? It lives in three-dimensional space, right? 3 times the number of electrons plus the number of nuclei, right? And even without time, if we're solving the time-dependent Schrödinger equation, there will be also time. Number of electrons 10, number of nuclei 5, right? So 15 times 3, this is 45, right? And then if you have 10 functions for each dimension, right? So it's 10 to the power 45. That's the number of coefficients in this expansion. Okay?
So we're just treating the nucleus as a point.
No, we're treating them as quantum particles, right?
Okay. So I was just, when you said nucleus, I was thinking, I guess, nucleons, like neutrons and protons, and then I was thinking.
Oh, that,
neutrons.
okay, so
I was
that's,
overthinking it.
all right, that's the same. If you, yeah, well, I don't treat nucleons separately, right? I'm not considering the kind of nuclear problem. But when we say nuclear problem in chemistry, we mean the dynamics of nuclei. Okay, so molecular dynamics. And we separate two subsystems, usually electrons and nuclei. And then if we're interested in dynamics, where the carbon goes, when hydrogen goes this way, then we need to, well, keep all these variables in 3D, right, in our wave function. And so then our wave function, our psi, will contain from 1 to 45 arguments, right? And then if each argument is represented by some, well, linear combination of, well, essentially by basis set with 10 functions, then in order to represent the whole thing, you would need to have 10 to the power 45 functions. And as we saw, when we have n functions for 1D problem, the Hamiltonian was the matrix n by n. In the 2D case, the Hamiltonian will be n squared by n squared. And in this case, the Hamiltonian will be 10 to the power 45 by 10 to the power 45. Right? So it's a huge matrix, astronomical numbers. So that's why in physical chemistry, chemical physics, what people are interested in, they of course like to use variational approach. It's straightforward. You just write algebraic coefficients, and eventually that becomes kind of a eigenvalue problem, right, to solve. And computers and there are lots of programs, software to solve the eigenvalue problem. So it can be efficiently done, but of course not for the matrices of this size. And this is not the largest molecule we need to deal with.
We have 10 to the 45. That means we're using 10.
Yeah, sorry, they got the joke about the molecule. Yeah,
so that 10 that we're using as a base, that means we're using 10 basis functions for each
dimension.
For each dimension. So we could use more if we want more accurate.
That's right. That's right. Yeah.
Okay, so that would be one way to reduce the computation, but at the expense
That's right.
of accuracy.
Yeah, exactly my point. So one way, well, there are two ways to reduce the complexity of the problem. First is you reduce the number n, right? N goes down, but accuracy doesn't suffer, right? And the second way, even more efficient way, is reducing the number of degrees of freedom, right? That you consider at one time. Okay. So here, for example, for the two-dimensional particle in a box or two particles, if you can somehow reformulate the problem so that you are treating one variable at a time, that would allow you to optimize only 10 coefficients instead of 100 coefficients, right? So those are the two ways: more efficient basis set that requires less functions in expansion per dimension, and separating some degrees of freedom. Maybe, sometimes it requires rotation, saying that if you have two variables in the classical physics, then you can write down things in terms of motion of center mass, and then the internal motion, right? And if there is no coupling between center of mass motion and internal motion, then the problem becomes exactly separable to the dynamics of center mass and then the internal motion. So unfortunately for molecules, center mass kind of can be separated, but that's only one variable. You can forget about the overall translational motion of the molecule, right? Well, actually, technically, it makes our life easier by free coordinates because you have x, y, z coordinate of center mass. But then internal coordinates still need to consider all electrons, all the nuclei. Then you approximately can remove the rotations, but then there's still electron motions and the internal vibrations. Those cannot be separated exactly, but we will discuss the ways to separate them approximately with a good level of approximations. And so one of them is so-called Born-Oppenheimer approximation. Right, so that separates electrons from nuclei. Right? And it does it approximately, but the approximation is pretty good. Now, the way it does it is tricky, okay, for the following reasons: that electrons and nuclei, they cannot live without each other, right, in a way that will be similar to what they do in the molecule, okay, because electrons are negatively charged and nuclei are positively charged. So if you have, based on just the classical electrostatics, electrodynamics, if you have the same charges, then they will just fly away, right? And then you need to have them together. But to have them together, you need to solve the equations which are more complicated than when we separate them, right? So there is a easy way, there is a way out of this. And I will illustrate that first on a model problem. We consider, again, particle in a box with two variables, x and y. And let's assume just that this potential, Vxy, is very strong. Okay? So we cannot neglect it. It really changes profoundly the wave function. But what we can do, and that's the key to understanding of Born-Oppenheimer approximation, is we cannot put the potential into the Hamiltonian, say, let me be more specific. So this is a full Hamiltonian x, y, right? And it has h1 for x. So this is kind of analog for electrons, say, plus h2 analogs for the nuclei. This is a kinetic energy of the electrons and nuclei. Then there are potential energies of interacting with each other. Well, electrons with electrons, nuclei with nuclei, right? Plus this V12 term, which is very strong, and we cannot neglect it, right? So essentially, what we did before is a very simple-minded approach where we obtain our functions phi's from the solution of individual problems, h1x acting on the phi I of x, and then it gives us ei phi x, right? So h2y acting on the, okay, I'll call it phi I tilde. These functions are made, well, they're different, energies are different. So this is not very efficient because V is very large. Okay? But doable, potentially. Right? Now, as a somewhat of motivation for the change of the construction here, I will just massage this expression a little bit more, the one that is not very efficient. So I will separate I and j summations in the following way. So I first sum j's. All right, so I first sum j's, and whatever I get after summation of j doesn't depend on j anymore, and I will call it, it has I subscript though, and depends on y, right? So this is some function that depends on I and y. And there is no approximation, so we just rearrange the summation here. I phi I x chi I y. Completely exact. Why? Well, okay, so now this form is closer to what is going on in Born-Oppenheimer. Why did I write it? Just to show that in this form, which is also exact, these two components are not equivalent. This one is still can be chosen the way we want. Okay, so this is a free component that it can come out of this expression or out of any h of x, any h of x I want. So this can be eigenfunction of h of x, whatever h is. So I'm free to choose this as my basis. This component, though, contains the coefficients and contains another basis set that is also kind of we have a freedom to choose that basis. But the coefficients, they are fixed based on the fact that this guy must be an eigenfunction of the total problem, right? So in that sense, there is less freedom, or you can say that there is no freedom in choosing the chi's. Okay, but there is still freedom in choosing of the x basis. Now, as I said, this is closer to the Born-Oppenheimer because what is going on in Born-Oppenheimer, we choose first in a more efficient way these functions, and then we will write equations for the second component. Okay, so that's the plan here. And to choose more efficiently these phi I functions, the key is to choose the Hamiltonian correctly that will generate these functions. As we talked, this H1 Hamiltonian is relatively poor. If we go to the molecules, right, it doesn't account for the nuclei at all, right? Now, to account for the nuclei, the Born-Oppenheimer way, and I will call it H1 tilde, will be the construction where it incorporates H1 of x, and then it also has V12 x, y. And I don't put the commas, but rather I put semicolon to kind of emphasize a different nature of y in this Hamiltonian. It's a parameter rather than variable.
So x is a function of y?
X is a variable.
Yeah.
So say this h of 1 of x in the case of in the molecules, it can have differential operator with respect to x, right, plus some potential function with respect to x. But this guy, it only has can have x as a variable, so it also can have differentiation, can have functions of x. But y is a fixed parameter, so it is a constant essentially. It's treated as a constant. It's not a variable. One way to think about this is, say you have xy space, right? This is x and this is your y. And then in practical terms, we discretize y, right? Have y1, y2, and so on, yn. And for every y, we have this h1 tilde Hamiltonian. So this one is h1 x y n tilde. This one has h1 tilde x y 1. So if this is number, say 2, and this one is 10, right? So this kind of another subscript for this Hamiltonian. You can also write it as h1 tilde comma 10 of x, and this one is h1 2 x, right? So it's just multiple Hamiltonians. They all different depending on what y is. Okay, so it's a parameter. It's an indexation essentially of these Hamiltonians, but they have all the same structure. Okay, what do we achieve by creating this Hamiltonian? Is we're bringing the potential, the one that is very important, the potential into the definition of what our phi of x functions are. But the cost is that we need to treat y as a parameter. Okay, so it's going to be always there. All right, so one analogy is with this U operator that we considered before, the time-dependent case of the Hamiltonian diagonalization, right? So y is like a time dependence, because depending on the parameter time, the functions which are eigenfunctions of this Hamiltonian, this can be thought as our Hamiltonian before, where y is time, so it depends on y parametrically, right? So different y, different Hamiltonian. And then the eigenvalues will also be y dependent because, well, they are following from the Hamiltonian. Okay. Now this is our setup, and this is pretty straightforward actually. Like, we know what v12xy is. We know what h1 of x is. So this presumably is just a particle in the box. So this is just a standard particle in the box Hamiltonian. This is an extra term. And we can solve this for every y. So we pick y, and we solve this Hamiltonian, this equation. Because picking y for the potential that we had was alpha xy, right? So I is substituted by some number, then essentially you get a different constant alpha, right?
So y is kind of like a continuous index.
That's right.
Similar to how we have, if we want to transform like our space basis function into momentum.
Mm-hmm.
We have a continuous
That's right.
index in that sense.
Yeah, absolutely. Now, we're almost done, because all we need is to find these guys, and we will solve the problem completely. Chi y's. Now, how do we do that? We use this Dirac's projection approach. So we know that total wave function should satisfy this equation. And actually, you can try it at home. The equations will be very similar for this case. So the only difference is the right-hand side, and that's the easiest part, because here and here there is no operator. Well, at least there is a time operator here, but it doesn't create off-diagonal terms usually. It is diagonal operator. So that makes the whole thing easier. But let's just stick to this and derive what the chi's will be. So if we now remember that, okay, so this is our h. This is our h, right? And our psi is this. With the only difference that now we have, let me just specify what psi is, really, because it's slightly different than this. It now has phi i's that depend parametrically on y. So we still have the summation over I, phi I, x, y, chi I, y. So when we are looking at the problem in general, like in the global problem, y here will not be anymore as parameter. It will be a variable as well. Because we already done solving this problem, and only for the x part we fixed y. But when we are going after y part, we considering that there is a part of the y dependence already here. Okay, and whatever is left, whatever is needed to complete the picture, we will obtain in the chi's. Okay, so the equation for the chi will be then h1 tilde plus h2. That's now our h, because h1 tilde already contains the v12 part, right? And then there will be summation over I, phi I, xy, chi I, y equals to e, summation over e there, and then the same thing, phi chi. Okay, and we do the projection. Our projection is done with respect to x variables, and we are projecting on, say, phi k. And the condition here is, since they are coming out of this equation, the functions are orthonormal with respect to integration with dx. And so we'll have h1 tilde plus h2 phi I, chi I, and summation over I equals to e integral dx phi k, phi I, chi I. Okay, so this will give us delta ki, again summation over I. Here we have two terms. First term is integral over dx phi k h tilde 1 phi I multiplied by chi I. And since the phi I is an eigenfunction of h1 tilde, and then this is I ei y phi I, right? Because this just comes out of this expression, right? And then this is not a function of x, so we can take it out of the integration. And what we have here is the e of y, the integral dx phi k phi I, which is again the Kronecker delta ki, and multiply by chi I y. Right, that's the first term. And the second term will be the integral over dx h phi k h2, and I'm skipping the conjugation because I'm assuming the functions are real. You can put conjugations there. The result will be very similar. So then we have phi I. And this is a tricky term. It's tricky because H2 depends on y, and it acts both on phi I, that depends on x and on y, and on chi I y. So it acts on the product. And there is this integral that integrates the x part. Now, the essence of Born-Oppenheimer approximation is to neglect the effect of H2 on phi I. Okay? And say, okay, this dependence on y is insignificant for H2. In molecules, H2y is a kinetic energy with respect to nuclei. So it's a second derivative operator on, essentially it's a second derivative of y. Right? It's a differential operator. And you are having a product of two functions that potentially depend on y. Okay? And so neglecting dependence on y in this term may not be that accurate after all, right? But the assumption here is that it's not going to create lots of trouble. And for the for simplicity, they usually kind of neglect that. Now, what we will do, we will keep this for now, all terms, and then I will write the simplified expression without these terms where H2 acting on the phi I. But for now, let's just keep them all. And what this term will generate is essentially, we can say it is H2 that is an operator Ki. It has subscript Ki, say, because we integrated the phi k and phi I functions, but it's operator because it depends on y. And then it's acting on the chi I y function. And then you have a summation over I. So that's going to be the second term. And let me write down the first term, which was here. That is clearly EI y chi I y and Kronecker delta Ki. So this was the left-hand side, and the right-hand side of this expression is E with chi I y and Kronecker delta Ki. Now we do the summation for these terms. We can remove summations and the Kronecker delta. For this we cannot for now. So we have still sum H2 Ki. Now you can think of this as an operator that has two subscripts, k and I, and it acts on y and on the function of y, plus so here's our equation to find chi functions. Okay? So, and this equation for every k. Right, so then we will have some energy at the right hand side. So it's like a eigenvalue problem because we have an operator. You can think this H2 is an operator, plus there is this diagonal Ki operator. Then it's acting on the chi1, chi2, chi-n components and giving you E chi1, chi-n components. Okay? And the difficulty actually stems from this H2 term that has subscript k and I, and so it has off-diagonal terms. That's why it's making this whole enterprise depend on the, well, have a matrix form. Okay? Now, if we do Born-Oppenheimer approximations, namely, if we neglect the fact that H2 also acts on phi, then the whole thing can be made diagonal and very simple. So say if the expression there is phi k, x, y, and then H2 acting on phi I, x, y, That's the term. And we consider now that this term is approximately equal to so H2 doesn't touch the phi I, it rather goes straight to the chi I. Then this again becomes Kronecker delta ki, right? And then the H2y is acting on chi I y, right? So then in this case, this expression is very simple. It's H2y plus E of ky acting on ky gives you energy. Right? So this is Born-Oppenheimer or adiabatic approximation because we neglected the action of H2 on the phi I. Strictly speaking, this term should also have a counterpart where the H2 acts only on phi, modifies phi, that becomes kind of new function that has both dependence on x and y, and we need to integrate with x, so then it won't give us Kronecker delta anymore. And whatever we have is a function of y acting on the chi. Okay? But we neglected that part. And that's why it becomes so simple. H2 only acts on chi, and this becomes a Kronecker delta, and the chi expression is very simple. So what we do then is a two-step process. First, we are solving this kind of electronic-like equation where we fixed y and solve for the x functions, and these are analogs of potential energy surfaces, the EIYs, right? And then we go and do the projection. If we approximate according to Born-Oppenheimer, then the equation for chi becomes this. Right? So compare this with a situation when we were dealing just with phi, well, these functions, right? Phi ix, phi jy, right? So those functions were coming from just x and y parts, and the y part was just h2y acting on some function of y, giving you eigenvalue times the function. But now we have this component, extra component, that comes because depending on y parameter, our functions, electronic functions, are changing. Okay? And that's the kind of simplest exposure to what Born-Oppenheimer is. It's essentially variational ansatz where we choose the basis set in a certain way without neglecting the coupling between between electrons and nuclei, or between x and y. We're doing a smart choice. And in every case, in every equation, this or that, we are only solving for one variable. Here we're solving for x, there we're solving for y. Okay, and then we combine the results. And it's exact. If we don't do the Born-Oppenheimer or adiabatic approximation, then this is exact. But in exact treatment, equations for chi's are quite complicated because all chi's are interconnected, okay, through the terms where H2 is actually acting on the phi's. All right, so let me write down what should be this term explicitly, and this term should be dx phi chi h2y acting on phi I xy. And so we stop here, and this becomes a function that depends on chi and I, and also y. And that function acts on the chi I y. So this is the term that we neglect, and we only left the term where h2 acts on chi. Okay, so this is a non-adiabatic terms. Now, another remark is that the Born-Oppenheimer and adiabatic approximation sometimes they used interchangeably, sometimes not. Strictly speaking, there is a school of thought that essentially in these terms there are some diagonal terms where I and k are the same, right? Some people, or in some literature, adiabatic approximation is distinguished from Born-Oppenheimer approximation because these diagonal terms that where k and I are the same, since they are diagonal, they don't make the matrix problem, right? So they still keep equations for different k's separated, but on top of h2y, you will have some extra terms coming from these essentially functions of I of fk of y, some extra additional potential terms, and when you include them, you call this adiabatic approximations, which is truly adiabatic approximation because you are confined to the adiabatic surfaces or electronic surfaces k, epsilon k, and you don't have non-adiabatic terms that couple k with some other components of chi. All right? And Born-Oppenheimer is considered to be just this without these extra terms. Okay? Questions? All right, so in the last 10 minutes, I can show you exactly what these terms are for molecules. Once we understand the basics on the two-dimensional problem, and for molecules, we have a Hamiltonian, which is kinetic energy of nuclei, kinetic energy of electrons, electron-electron, electron-nuclei, and plus VNN, nuclear-nuclear. So these are Coulomb interactions. And Ri, Rj, so those for electrons with positive sign, negative sign for nuclei. And positive sign for nuclear alpha. Okay, and then kinetic energy of nuclei, h bar squared divided by 2m alpha. Sum over alpha, and then for electrons, okay. So kinetic energies are differential operators. These potential terms are Coulomb operators. So Coulomb interaction between electrons and nuclei, that's the binding glue, right? And that's what.
Sorry, so Z sub alpha?
Those are the charges.
So alpha is electrons?
Nuclei. The big letters, big R's are for the nuclei, and the small R's for the electrons.
What is the alpha and beta?
Alpha and beta, there's indices for for different nuclei, like say just a numeration index. Okay. All right. So now our H1 tilde will be so-called electronic Hamiltonian that will contain all the terms but the nuclear kinetic energy. So it will contain electronic kinetic energy, it will contain electron-electron repulsion, electron-nuclear, and last but not least, the nuclear-nuclear part. So which is somewhat surprising based on the idea of what the electronic Hamiltonian is supposed to be about. Well, the left-hand side you can write down later. Don't worry about it. It's going to be online, and it's easy to find. So this part is though not making our life harder because it only depends on the nuclear parameters, right? So it's easy to fix the coordinates of nuclei in the consideration of electronic structure. Right? So this is called electronic structure problem when we solve HE, say F electronic with subscript I. So some of you have done calculations, right? So you set up the molecule and do electronic energy calculation for the fixed nuclear geometry. Yeah.
Is this for multiple electrons?
Yeah, it could be any number.
I'm just wondering, how come the potential for the electron-electron, like it just has 1 over, like,
Yeah.
Whereas the potential, I'm just still confused about that in Z. I thought that was the number of nucleons. Like,
No, Z are charges. You have a Coulomb interaction.
so how come there's no Z for the electron-electron interaction?
Because it's in atomic units where we assume that the charge of an electron is 1. Yeah, sorry about that. Yeah. So to be fully consistent, I guess I need to remove the mass of electrons and H, because in atomic units the H bar is 1, but the mass of nuclei are staying, right? So they are around 2,000 for hydrogen in atomic units, but mass of electron is 1, and charge of electron is 1 or minus 1, and yeah, Z's or Z's are charges. Yeah. Okay, so this gives us potential energy surfaces, so common in quantum chemistry, right? So that's the phi ix with the parameters y's. That's the analog of that. Then the nuclear problem. When we are solving for the nuclear problem, the total wave function then the total wave function becomes sum over I phi electron I chi I, the big R, right? So this is a total wave function, and when we solve for the nuclei, we have analog of H2 will be kinetic energy of nuclei. That's the differentiation with respect to big R's. Yeah, it's written there. And then, I guess I can write what is in Born-Oppenheimer approximation. Tn plus we have these guys, electronic surfaces. That's for K, R, Okay, this is a Born-Oppenheimer case. Well, now non-Born-Oppenheimer or beyond Born-Oppenheimer, what we are missing in Born-Oppenheimer is the following terms. So that will be integration over electronic variables I, kinetic energy of the nuclei K, and here the integration is done only over electronic variables. Because remember, when we project, we integrate only x part, not y part. So this, now I'm working on this more complex H2KI operator. All right, so this will be this acting on the chi kr. And if we now think about it, it will have multiple terms. Because we need to differentiate. When we differentiate, this is a second derivative, d squared dr squared, right? And I'm forgetting for some, but this is a differential operator that will act on the phi and also will act on the chi k, all right? And since there are two of them, there will be a whole slew of terms. So the two extreme cases are quite easy, right? So when you do double differentiation on this guy or double differentiation on that guy, right? And then there will be single differentiation on this, single on that, and there will be the opposite kind of order. So there will be two terms when you differentiate each of them. So this becomes fi and differentiation kind of, in order to say it stops at this, doesn't go further, I put this in parentheses, and of course there is h squared divided by 2m. And then there's a chi k of r. Okay? And then there will be term which we already accounted in the Born-Oppenheimer. It's phi I, phi k, and then double differentiation. All right, so this is a kinetic energy acting on the chi only. And then there will be another term where we differentiate this and this only once. And there will be two terms like that because it's a square. So then it's phi I over dr okay, and with 2, this term will be minus h bar squared divided by m. So this is the first, second, and this is the third term. Now Born-Oppenheimer takes into account this, but doesn't take into account these terms. Okay? Questions?
Can you just repeat that? Which terms does it take into account?
It does take into account only this term, because essentially what Born-Oppenheimer doesn't do, it does not differentiate the electronic functions in their parametric dependence on the nuclei, right? So that is what it, well, that's what makes Born-Oppenheimer so simple, because it neglects that. If you account for that, then once you differentiate these functions, they are not anymore orthogonal to this function. So you cannot neglect the coupling then. That's what well, complicates things if you account for these derivatives. So essentially, in the electronic problem, to make it more kind of smarter, you put the nuclear dependence, but then you suffer from that nuclear dependence because when you go to the nuclear equation, the nuclear derivatives will affect not only nuclear functions but electronics as well, right? and there will be extra terms. You're trying to be kind of smarter, like in this diagonalization problem. If you diagonalize at every time step, then your vectors will start depending on time, and then you need to differentiate them with respect to time. Right? So, but the advantage of that is, of course, you are getting more out of the electronic problem. They know where the nuclei are. They just don't account for their motion. Okay. All right. So I'll see you next Wednesday.